When we think about leaving our galaxy, we imagine an edge, a line, a clear boundary separating inside and outside. But the universe does not work that way. There are no walls of stars, no signs marking the end of the territory. The Milky Way is not a solid disk floating in nothingness. It is a diffuse structure. It has a dense core. It has spiral arms where stars are born. It has regions where gas is abundant and others where barely any matter remains. And beyond the visible glow, there is something even larger, a halo. The galactic halo cannot be seen with the naked eye. It is composed of ancient stars, globular clusters, and extremely tenuous hot gas. It extends far beyond the disk we usually draw on maps. If we could observe in X-rays, we would see a corona of gas enveloping the galaxy like a colossal atmosphere, but even that is not the end. Beyond the visible halo lies an even more massive and mysterious structure, the dark matter halo. It does not emit light. It does not absorb light. It does not interact with radiation as ordinary matter does, yet its gravity holds the galaxy together. The stars at the edges rotate far too fast for the visible mass we observe. Something else is there, something with weight. When we speak of leaving the galaxy, are we leaving the disk, the stellar halo, the gas corona, or the invisible halo that dominates the total mass? There is no defined boundary. There is a gradual decrease in density. The stars grow sparse. The gas becomes almost non-existent. Gravitational influence slowly dissolves into the presence of other structures. And here, the first real mystery appears. Galaxies are not isolated. The Milky Way has satellite galaxies. Some are visible to the naked eye in the southern hemisphere, such as the Magellanic Clouds. Others are barely detectable dwarfs with only a few million stars. Many of them are being stretched, slowly torn apart by gravitational tidal forces. There are no explosions, no crashes like those of two cars. When two galaxies interact, the stars almost never collide with one another. The space between them is enormous. What happens is something else. Trajectories change, systems deform, long thin stellar streams form, like luminous scars recording past encounters. Some of these streams surround our galaxy. They are remnants of smaller systems that were absorbed. Each one tells a story spanning millions or billions of years. The Milky Way grew by devouring smaller structures, and it still does. So, have we truly left when we move beyond the bright disk? No. We have only entered the region where galaxies interact. Gravity does not stop at the visible edge. It extends outward. It overlaps with that of other nearby galaxies. Influences blend together. Space is not divided into sealed compartments. Our next level of reality is not the void. It is the neighborhood. We live in the local group, a collection of more than 50 galaxies that share a common gravitational destiny. They are not scattered at random. They move under mutual influence. They approach, they recede, they orbit shared centers of mass. The two largest dominate the system, the Milky Way and the Andromeda Galaxy. Both possess similar masses. Both have gigantic halos of dark matter that are already interacting, even though their disks are still separated by more than 2 million light-years. That number seems enormous. It is for human experience. But in cosmic terms, it is an intimate distance. Andromeda is approaching. Not at great speed in everyday terms, but enough for a future collision to be inevitable. Within billions of years, both galaxies will pass through each other. There will be no instantaneous explosion. There will be a slow dance. The disks will distort. Tidal tails will form. Orbits will change. Eventually, a new elliptical or lenticular galaxy will emerge as the result of that prolonged merger. What is interesting is not the future spectacle, it is the fact that this process is common. Galaxies are not static objects, they are evolving entities, they grow through mergers, they transform through interactions. The universe on large scales is dynamic, and leaving a galaxy does not mean entering the void, but entering a network of gravitational relationships. The local group itself is not isolated. It is part of a larger structure. It is gravitationally linked to other groupings. It moves in a preferred direction. There is a cosmic flow. But before moving toward larger scales, something essential must be understood. Galaxies do not have sharp edges because matter is not distributed abruptly. It is organized in gradients, in structures that blur into one another. The space between galaxies is not completely empty either. There is tenuous gas, there are particles, there is relic radiation from the Big Bang filling the entire cosmos. Even in apparently deserted regions, the density is not zero. Leaving the galaxy is a matter of scale, not of boundary. If we widen our perspective enough, the bright disk of the Milky Way becomes a minor detail. The halo fades. Satellite galaxies become points. The local group appears as a small concentration in a much vaster region. And then an unexpected image emerges. On larger scales, galaxies are not distributed uniformly. They cluster in filaments, they form clusters, they leave nearly empty regions between them. The universe, when observed across hundreds of millions of light years, resembles a network more than a homogeneous cloud. That network was not designed, it was not drawn. It arose from tiny fluctuations in the early universe. Small variations in density that grew under the action of gravity over billions of years. Every galaxy, every group, every cluster is a consequence of those initial seeds. And here, a deeper question appears. If the universe is homogeneous on large scales, as the cosmological principle states, why do we see such marked structures? To what extent does that network truly respect the idea of statistical uniformity? Leaving our galaxy does not take us into the void. It takes us into a cosmic architecture, an architecture that does not end at the local group, an architecture that connects entire superclusters through filaments of matter, an architecture that contains gigantic voids, regions where there were almost no galaxies. The local group. When we zoom out a little on the map, the Milky Way no longer appears alone. Neighbors emerge, some large, others almost invisible, all trapped in the same web of gravity. That collection is the local group. A group of galaxies is not just a cluster of nearby points, it is a gravitational family. The galaxies of the local group share a common long-term destiny. Their motions are not random, they respond to the combined pull of all the mass distributed across the region. Visible matter, gas, dark matter, everything counts. At the dynamic center of this cosmic neighborhood stand two giants, our Milky Way and the Andromeda Galaxy, each with hundreds of billions of stars, each wrapped in a halo of dark matter extending far beyond the visible disk. Those halos overlap. They do not collide like solid objects, but their gravitational fields interfere and shape the motion of everything else. The third major member is the Triangulum Galaxy, smaller than the other two, but not a dwarf. It has its own disk, its own star-forming regions, its own clouds of gas. Together with the Milky Way and Andromeda, it forms a kind of gravitational triangle, where each responds to the presence of the others. even though they are separated by millions of light years. Around these three large galaxies gather dozens of dwarf galaxies. Some orbit directly around the Milky Way, others revolve around Andromeda, several display stretched tails as if they were slowly being pulled apart. They are fragile systems. A prolonged gravitational tug can dismantle them into streams of stars that end up bathing the halo of a larger galaxy. The local group has a characteristic size. Beyond a certain radius, the combined gravitational force of its galaxies no longer dominates. There begins the transition to another scale of organization. Within that radius, however, galaxies remain bound. They may drift slightly apart, oscillate, orbit common centers of mass, but they do not escape easily. This detail is important. When we look far away, we see that the universe is expanding. Galaxies recede from one another on average, yet within a group, gravity can overcome that expansion. The local group is an example. Although the cosmos as a whole stretches, galaxies bound by gravity form stable structures. Groups and clusters are islands where expansion is partially neutralized. The future of these islands is marked by slow collisions. We know that Andromeda is approaching the Milky Way. We know that in a few billion years their disks will merge. This is not an exception. It is the usual way groups evolve. Large galaxies grow by consuming smaller ones and merging with each other. For that reason, we can say that the local group has a destiny. It is not a static collection. It is a system in process. In the past there were more dwarf galaxies. Some have already been absorbed. We know this from the streams of stars that cross the halo. In the future, there will be fewer individual galaxies. A couple of large systems will remain, resulting from several mergers, perhaps accompanied by a few resistant dwarfs. Among the galaxies of the local group, there are not only stars. Intergalactic space contains very tenuous gas. There is also a hot medium, probably linked to the extended halo of dark matter. This gas can be detected by its effect on background light or by X-ray emission. It is not a perfect vacuum. It is a physical environment where galaxies move, lose material, and exchange it. Motions within the local group are organized around a common center of mass. If we could see vector by vector, we would see curved trajectories, falls, deviations. However, when we take an average, we notice something else. The local group as a whole also moves with respect to the cosmic microwave background. We are not at rest. Our entire neighborhood sails through a larger structure. This double level of motion is key. Each galaxy orbits within the group. The entire group moves within a broader environment. It is like a solar system inside a galaxy. There are internal orbits and at the same time a global orbit that carries the whole ensemble along. The scale changes, but the logic is similar. Moreover, the local group does not float in the middle of nowhere. It is embedded in a relatively flat structure of neighboring galaxies that astronomers sometimes call the local sheet. Beyond it appears the Virgo cluster. Still farther away, other clusters and superclusters. Each step reminds us that any edge we define is provisional. There is always another level. If we think of the local group as a neighborhood, we can imagine gravitational avenues connecting it with other neighborhoods. These avenues are not constructed roads, they are preferred directions in space where the density of matter is greater than average. Along those directions, galaxies travel, pulled by the combined gravity of all the concentrated mass. This is where the idea of invisible highways makes sense. When we observe the velocities and positions of many galaxies in a broad region, we detect patterns. Some align, others share components of motion toward the same places. It is not by chance. They respond to the same gravitational landscape carved by visible matter and dark matter. The local group follows those rules. It does not choose its destiny, it obeys it. Its motion is conditioned by more massive clusters and by nearby large voids. Low-density regions that, in a sense, push in the same way that high-density regions attract. The combination of both defines the routes we follow. The cosmic web. If we keep moving away from the local group, something curious happens to our intuition. We expect to see galaxies scattered like random points within an enormous volume, a uniform cloud, an elegant chaos, but when we look closely, the universe does not look like that. To see the real structure, isolated photographs are not enough. We need three-dimensional maps. This is achieved by measuring the positions and distances of thousands, then millions of galaxies. In the sky they appear as flat points, but redshift gives us a clue about how far away they are. By combining these data, a new image emerges. What appears is not a cloud, it is a network. Galaxies cluster, forming long filaments. These filaments intersect at nodes where clusters are denser. Between filament and filament, vast voids open up, regions where there are very few galaxies. The result resembles a sponge, a honeycomb, a three-dimensional spiderweb stretching across the entire observable universe. There are no straight lines drawn with a ruler. There are no perfect patterns, but neither is there pure chaos. There is a statistical organization. At certain scales, motifs repeat, nodes, strands, gaps, as if the universe had texture. That texture was not imposed from the outside. It arose from something very simple. In the early universe, shortly after the Big Bang, matter was not distributed in a perfectly uniform way. There were small density fluctuations, regions just slightly denser than average, regions just slightly less dense than average. Gravity amplified those tiny differences. Where there was a little more matter, the attraction was stronger. That attracted even more matter. Over time, those zones became denser. In the less dense regions, the opposite occurred. Matter flowed toward neighboring zones. Thus, slowly and cumulatively, the contrasts were reinforced. The expansion of the universe did not stop this process. It modulated it. While space was expanding, matter was trying to cluster. The result is precisely that cosmic web, a struggle between global expansion and local collapse. Between the stretching of space and gravitational infall, the filaments are the main routes of that flow of matter. There, galaxies, gas, and dark matter concentrate. At the nodes where several filaments meet, massive clusters of galaxies emerge. Between them, voids open up like giant bubbles where the density is very low. Scale is important. At relatively small distances, on the order of a few million light-years, the distribution of galaxies is very irregular. As we enlarge the volume, the network continues to appear. But when we reach hundreds of millions of light-years, the pattern begins to average out. Here, the cosmological principle comes into play. This principle is a simple but powerful idea. It states that, at sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that there are no privileged regions in terms of average density. Isotropic means that, viewed from any point, the statistics of matter look the same in all directions. It is clear that on small scales this is not true. Here we have a galaxy, there a cluster, beyond that a void. But if we take enormous volumes and compute averages, the differences become smoothed out. The structures do not disappear, but they cease to dominate the overall picture. What matters is the average density over large regions, not the local details. The cosmic web fits this view. It is highly structured on the scale of groups, clusters, and superclusters, but when encompassing gigantic volumes, its statistical pattern becomes uniform. An everyday comparison would be looking at a sponge up close and then from far away. Up close we see holes, fibers, irregularities. From afar we see a more or less uniform block. Now, that homogeneity is a statistical property. It does not mean that the universe has a perfectly repetitive design. It means that if we choose large regions at random, the average differences between them are not extreme. And here, a subtle nuance appears. When we observe the cosmic map with ever better instruments, we are constantly tempted to search for giant structures. Very long galaxy walls, superclusters connecting other superclusters. Filaments that seem to cross a significant fraction of the observable universe. It is part of human nature to detect patterns. The scientific question is not whether large structures exist. We know they do. The question is whether they are compatible with what we expect from a universe governed by the current laws of physics, seeded by early fluctuations and shaped by gravitational growth. Whether their size and coherence respect the scales at which the universe should become homogeneous. To answer this, astronomers combine real maps and digital simulations. The simulations take a given cosmological model and let it evolve. They reproduce the expansion of the universe, the presence of dark matter, the influence of dark energy, and the physics of gas. From this process, synthetic structures emerge that can be compared with those observed. Remarkably, in many respects, the simulations replicate the web well. Filaments, nodes, voids, clusters, not in every detail, but in their statistical pattern. This agreement reinforces the idea that the standard cosmological model, with its main ingredients, captures the essence of how the cosmos is organized on large scales. However, not everything fits perfectly at first glance. Some observations of very large structures have sparked debate. They are regions where the distribution of galaxies appears to form alignments or concentrations whose dimensions approach or exceed the theoretical limit beyond which we would expect homogeneity. When a too large structure is announced, what is at stake is not only its size, but its interpretation. It may be a coherent physical object. It may be a chain of independent structures that, when projected onto our maps, appear as a single one. It may also be a statistical effect, an extreme but possible example within the model, or it may be a clue that something is missing in our understanding. To distinguish among these options, everything must be re-examined. The way galaxies are selected in a sample, the way distances are calculated, the algorithms that define what counts as a structure, even the unconscious biases involved in searching for striking patterns. The map of the universe is not a static drawing, it is a dataset under constant revision. Every new deep survey adds galaxies. Every new redshift measurement refines the contours of the cosmic web, and every improvement forces us to reassess what we mean by filament, by cluster, by void. Meanwhile, the cosmic web remains one of the great achievements of modern cosmology. It shows us that the universe has memory. The position of each galaxy is not random. It reflects the history of the initial fluctuations and the time gravity has had to act. It also reminds us of something else. We are not at the center of that network. The Milky Way occupies a modest node within a filament that connects to other nodes. There is no privileged place, there is no up or down, only a structure that repeats with variations across billions of light years. As we map that structure with increasing precision, we begin to see details that were once invisible: subfilaments, microvoids, alignments, regions where density changes more abruptly than we expected. Each refinement of the map opens the door to new questions, and in those questions appears the next step of our journey. Mega structures galacticas. Once we accept the idea of the cosmic web, another problem appears. If there are filaments, clusters and voids, how large can these structures grow without the universe ceasing to be homogeneous on average? The standard theory gives us a clue. On scales of hundreds of millions of light years, density variations should begin to average out. We would no longer have special regions, but rather a uniform statistical pattern. That is the heart of the cosmological principle. We are not in a privileged place. From any point, on large scales, the universe should look similar. But observations always test beautiful ideas. As galaxy surveys became deeper and wider, striking structures began to appear. Very long chains of clusters. Regions where the density of galaxies was much higher than in neighboring areas. Apparent walls stretching across hundreds of millions of light years. The first reaction is to think we have found something that should not exist. A structure that is too large. An object that breaks the principle of homogeneity. However, the story is always more complicated. First, we must clarify what exactly structure means. It is not a solid wall of galaxies. It is not a single piece. Often it is a collection of clusters, filaments and groups that, on a map drawn with certain criteria, appear connected. The way we define that connection matters greatly. In practice, algorithms are used to detect structures. These algorithms decide when two galaxies belong to the same grouping. For example, if they are below a certain separation distance, or if they belong to a region whose density exceeds a given threshold. Changing the threshold changes the size of the identified structures. Moreover, our galaxy samples are never perfect. We do not see all galaxies. We do not see them with equal ease in every direction. There are brightness limits. There are regions of the sky obscured by the Milky Way itself. There are distance errors. All these factors affect how structures appear on maps. That is why, before declaring that something is too large, we must ask how the catalogue was constructed, which galaxies it included, what criteria were used to link them, and above all, how likely it is to obtain something like this purely by statistical chance within the standard model. Here, cosmological simulations come into play once again. We take a simulated universe that complies with our theory. We observe it with the same limitations as a real telescope. We apply the same algorithms, and we count how often structures of a given size appear. If apparently rare events recur with some frequency in the models, then they cease to be profound anomalies. Even so, there are cases that are unsettling, not so much because of an isolated number, but because they seem to suggest alignments or patterns on scales where we would expect more randomness. For example, regions where many galaxies and quasars are concentrated in a narrow strip of space, or prefer directions that seem to mark an axis in a universe that, in principle, should not have one. Here another key concept appears: cosmic variance. The observable universe is large, but not infinite. We can only see a sample. That sample may, by chance, contain more striking structures than the global average. Not because the physics is different, but because we are in a particular fragment of the whole. It is like looking at a portion of a sponge and finding, right there, a hole larger than the average. Cosmic variance reminds us that we may be observers of a somewhat unusual region without that invalidating the general model. But it also reminds us of the limits of what we can conclude from a single observed universe. We do not have other universes to compare with. The challenge then is to quantify to what extent a particular structure strains the model. Is it just an extreme but possible case? Or does it require a serious revision of our assumptions? To answer that, hard statistics are needed. Headlines are not enough. Behind many discussions about impossible superstructures lie differences in the interpretation of data. Sometimes new analyses with more complete catalogs reduce the apparent size of these structures. What seemed to be a single entity turns out to be, in reality, a superposition of several. On other occasions, the structure is confirmed, but it is shown that within the margin of variation of the standard model, it is rare but not impossible. There is, however, a more philosophical point. The very fact that we are searching for the maximum limits of cosmological structures is a sign of the model's maturity. When a theory becomes established, anomalies are no longer nuisances but tools. They show where there may be new physics, or where our observational and analytical methods still carry biases. In this context, giant structures not only put the principle of homogeneity under strain, they also offer an opportunity to revisit other ingredients. For example, the amount and distribution of dark matter, the way initial perturbations grew, the possible influence of dark energy on the history of gravitational collapse. It is no coincidence that many of these discussions are connected to the expansion of the universe. The speed at which space stretches and how that speed has changed over time directly influences how long matter has had to cluster together. If the expansion was faster during certain epochs, the growth of structures slowed down. If it was slower, structures were able to grow larger. This leads us to an inevitable question. When we say that a structure is too large, are we not, at some level, assuming a particular history of expansion? And what if that history is not exactly what we think it is? For years, the standard model described an accelerated expansion dominated by a dark energy that is constant in time. A kind of uniform negative pressure pushing the fabric of space. But today, more flexible scenarios are being explored. Researchers are studying whether that energy might vary slightly. They are analyzing whether small adjustments could resolve some tensions between different measurements. Giant structures, long filaments, massive clusters are no longer mere curiosities. They are fossil records of how matter has grown over time. If we reconstruct their distribution and evolution with precision, we can infer how cosmic expansion behaved during different epochs. In other words, the anomalies in the galaxy map become indicators of the universe's dynamic history. What appears to be a problem of size may conceal a problem of pace. For now, the standard model holds. It explains most of what we observe quite well. However, each new galaxy survey adds details that force us to refine it. Sometimes those corrections are small. Other times they open the door to bolder hypotheses, modifications of gravity, non-constant dark energy, new physical components. None of this is settled. Contemporary cosmology lives precisely on that edge, between confidence in a theoretical framework that works and the expectation of finding cracks that point the way to a more complete physics. Structures that seem too large place us exactly at that point of tension. They do not overthrow the model, but neither do they allow us to relax. They compel us to examine the data more carefully, to improve the maps, to question the assumptions hidden in our methods, and to follow that thread, we must shift our focus. An accelerated expansion. So far, we have looked at the shape of the universe, filaments, clusters, voids. But that shape only makes sense if we understand something deeper, the rate at which space itself stretches. At the beginning of the 20th century, the dominant idea was different. Many physicists imagined a static universe. It neither expanded nor contracted, it simply was. When the equations of general relativity suggested otherwise, they were adjusted with an extra term to keep it still. Then came the observations. By measuring the redshift of distant galaxies, a clear pattern emerged. The farther away a galaxy is, the faster it appears to be receding. That relationship, which we now call Hubble's law, revealed something surprising. It is not that galaxies are shooting off in all directions from a central point. It is space itself that stretches. Distances grow. The galaxies themselves may remain at rest locally, but the fabric in which they are embedded expands. For much of the 20th century, the idea of an expanding universe became central. However, it was assumed that this expansion was slowing down over time. That makes sense. Matter attracts matter. Gravity tries to slow the stretching of space. Depending on the total amount of matter, the universe could expand forever, though ever more slowly, or even halt and collapse in the future. The greatest surprise came later. In the late 20th century, astronomers began using Type 1a supernovae as standard candles. These are stellar explosions in binary systems that reach a fairly uniform peak brightness. By measuring how bright they appear from here, we can estimate their distance. By measuring their redshift, we learn how much space has stretched since the light was emitted. When many of these data were combined, something unexpected was found. Distant supernovae were dimmer than they should have been, not because of dust, not because of simple errors. They were farther away than expected if the expansion was slowing down. The only consistent explanation was different. The expansion of the universe not only continues, it accelerates. It is like throwing a stone upward and discovering that instead of slowing down due to gravity, it begins to rise faster and faster. Something in the cosmos acts like a kind of negative pressure. It pushes space to stretch more rapidly. We call that something dark energy. The name does not say much. It simply acknowledges that it is a form of energy we do not see directly, and that it has large-scale effects on expansion. It does not shine. It does not clump into galaxies. It appears to be distributed uniformly throughout space. The simplest model is a cosmological constant, a fixed energy density associated with the vacuum itself. Every portion of space would contain the same amount of dark energy. As the universe expands and gains volume, the total amount of that energy grows. that extra energy drives the expansion even further. The result is a self-reinforcing loop, but that is only the simplest model. The big question is whether dark energy is truly constant or whether it could change over time. That difference is crucial. If it is constant, the future of the universe resembles a gentle yet inexorable increase in acceleration. If it changes, the fate may be different. How do we investigate something we cannot see directly? By observing its effects on three major fronts. The cosmic microwave background radiation, which shows us the universe when it was very young. Baryon acoustic oscillations, which act as a kind of cosmic ruler to measure large-scale distances. And the history of structure formation, that is, how clusters and filaments grow over time. Each of these methods gives us clues about how the universe has expanded in different eras. It is like having photographs taken at different moments in a race and trying to reconstruct the speed in each segment. If dark energy were a perfect constant, all those data sets should align with the same value. If they do not, there may be richer details involved. Current observations indicate that dark energy represents about 70% of the total energy density of the universe. Dark matter accounts for another large fraction. Ordinary matter, the matter of stars, planets, and visible gas, is only a small part. It is a strange distribution of roles. What we know best is not what dominates the large-scale destiny. When we speak of accelerated expansion, we are not saying that nearby galaxies are moving away from us at extreme speeds. On the scale of groups or clusters, local gravity prevails. The galaxies of the local group, for example, are gravitationally bound. Dark energy becomes important when we look at distances of hundreds or thousands of millions of light years. There, the accumulated effect of the dynamic vacuum begins to outweigh the attraction of concentrated masses. There is something almost paradoxical about this situation. Dark energy is invisible, uniform, and smooth, yet its influence is felt in the ultimate architecture of the cosmos. It determines how much time matter has to gather into structures. It sets the pace at which certain scales freeze out. It decides whether future clusters will form or remain forever separated by a space that stretches too quickly. From a theoretical point of view, dark energy is a real headache. If we interpret it as quantum vacuum energy, estimates from particle physics yield absurdly high values, far from what we infer observationally. It is a gigantic discrepancy. What we measure is vastly smaller than what simple vacuum theories predict. If instead we think of it as a dynamic field that changes over time, other difficulties arise. We must explain how it evolves. Why does it have the value it has today? Why did it begin to dominate precisely at this stage of cosmic history and not earlier or later? This is the so-called coincidence problem. It seems that we live at a moment when dark energy and matter have comparable densities, whereas for most of the past and future, this will not be the case. Another possibility that has been explored is that there is no new form of energy, but rather that we are misinterpreting gravity on large scales. Modifying general relativity to explain the acceleration without invoking dark energy is tempting but difficult. The theory of gravity has passed many tests on small and intermediate scales. Any modification must preserve those successes, while at the same time generating acceleration on large scales. There is no single proposal that clearly accomplishes all of this. For the moment, dark energy as an effective component works very well to describe the data. It is a useful tool, but we do not know what it physically is. It is a name that conceals our ignorance. In fact, although we use the word energy, what we really have is a parameter in the equations, a term that adjusts the rate of expansion. We have measured with considerable precision what its value should be today. What is under discussion is whether that value is exactly constant or whether it has been slowly and almost imperceptibly adjusting over time. The Hubble tension. If we want to understand the universe beyond the Milky Way, we need a ruler, a rhythm, a unit that tells us how fast space is stretching today. That number exists. It is called the present-day Hubble parameter. But there is a serious problem. Depending on how we measure it, we obtain different answers. At first glance, it seems like a technical issue, a disagreement between research groups, a detail that will be smoothed out with time. However, the discrepancy does not disappear. It grows in statistical significance, and that opens the door to something deeper. Either we are making a mistake somewhere in the process, or the model of the universe is missing a piece. To understand the conflict, we must see that we are not talking about one method to measure expansion. There are at least two major paths, both respectable, both complex, both built upon long chains of calibrations. The first path looks at the nearby universe. It is a bottom-up approach. It is based on constructing a distance ladder. In astronomy, we cannot stretch a measuring tape to a galaxy. We measure subtler things. First, objects whose distance we know geometrically, such as certain nearby stars. Then, using them, we calibrate new, more distant rulers. And so, step by step, we reach distant galaxies. This ladder includes Cepheids, variable stars whose intrinsic luminosity is related to the period of their brightness. It also includes other standard candles, such as red giant branch stars or the so-called JAGB stars. With these references, we calibrate the true brightness of Type 1a supernovae in relatively nearby galaxies. Then we use even more distant supernovae to trace the relationship between distance and redshift. When this process is completed, we obtain an estimate of today's Hubble parameter. With current data, this local method usually yields a relatively high value. The expansion of the universe measured this way would be somewhat faster. The second path is almost the opposite. It looks at the very young universe. It is a top-down approach. It starts from what we know about the early cosmos and the standard cosmological model. It uses the cosmic microwave background radiation, baryon acoustic oscillations, and other traces to reconstruct how expansion has proceeded from primordial times to today. The background radiation is the fossil light of the universe when it was a few 100,000 years old. In it, we see small temperature variations. Those variations encode information about the density of matter, radiation, and the global geometry. By fitting a model to those data, we can infer how the Hubble parameter evolved over time. If we assume that the lambda CDM model is correct, we also obtain a value for the current expansion rate. With this method, the Hubble value tends to be lower. The universe would be expanding today slightly more slowly than local measurements indicate. The difference is not enormous in absolute terms, but it is statistically significant. It can no longer be easily explained as a simple rounding error. These two ways of measuring the same number are like two clocks, one placed in the living room, another hanging from the deep past. Both should agree if the mechanism connecting them is the standard cosmological model, but they do not, and the better we measure, the clearer the discrepancy becomes. The first reaction is to check the clocks. On the local side, possible systematic errors have been explored. Are we calibrating Cepheids correctly? Does dust affect the measured brightness? Are we choosing representative galaxies? Are there environmental effects we are not considering? Different groups have refined their techniques, used other standard candles, and changed instruments. The figure adjusts, but it does not drop drastically. On the early universe side, something similar happens. The background radiation data are re-examined. Variations in the model parameters are tested. The codes that transform observed fluctuations into cosmological parameters are checked. Other traces are studied, such as the acoustic oscillations measured in the distribution of galaxies. The result, again, becomes more precise, but it does not jump towards the local value. The more work is done, the clearer it becomes that the tension does not disappear on its own. Beyond a certain point, the question changes. It stops being "where is the error?" and becomes "what if it is not an error?" That is, what if one of the basic assumptions we use in one method or the other needs to be revised? One possibility is that an ingredient is missing in the physics of the early universe. If the energy content at that time was slightly different from what we assume, the way structures formed and the way acoustic oscillations propagated could change. That would alter the inference of the current Hubble value from the background radiation without affecting local measurements. Another option is that dark energy has not always behaved as a constant. A small change in its evolution over time could reconcile part of the tension. But this requires that the adjustments be compatible with many other observations, not just the Hubble number. It is not enough to turn a knob in an equation. Every change has cascading effects on other observables. The idea of additional types of matter has also been explored. For example, some form of extra dark radiation in the early universe. That would change the rate at which the cosmos expanded in its first moments and could alter the correspondence between primordial patterns and the current value of their expansion. Again, it is not easy to fit this in without breaking other successes of the model. In parallel, the possibility remains that there are biases we still do not see in one of the two approaches. It is not ruled out that, with new data and techniques, one of the clocks will eventually correct itself and move closer to the other. It is the tension between humility and ambition, between assuming that we do not understand everything and allowing ourselves to dream of new physics. What matters is that, in any case, the Hubble tension touches the heart of cosmology. We are not discussing a peripheral detail. We are discussing the current rate of expansion, which enters into all the equations that describe distances, ages, and sizes on large scales. To understand the mysteries that await beyond the Milky Way, this tension has a direct consequence. When we talk about distant extragalactic structures, when we estimate how far away they are, how large they are, and how much they have evolved, we necessarily use a conversion between redshift and distance based on a value of Hubble. If that value changes even slightly, the scales we assign also change. It is not that galaxies move from place to place. What changes is our map. The way we translate observational information into a three-dimensional image of the cosmos. A somewhat faster or slower expansion affects the age we attribute to certain structures and the time they have had to form. In other words, the Hubble tension is not a numbers game for specialists. It is a reminder that even our basic map of the universe has room for revision, that the distances we assign to the mysteries beyond the Milky Way are, at some level, built upon a scale that is still being adjusted. Meanwhile, observation continues to advance. New telescopes and surveys attempt to measure the expansion with complementary methods. Gravitational waves from binary mergers could become future standard sirens. More extensive maps of galaxies and quasars refine acoustic oscillations as a ruler. The idea is to add new clocks to the comparison. The incomprehensible growth of galaxies. When we observed the distant universe with earlier telescopes, the picture was limited. We saw faint points, poor spectra, signals barely sufficient to say, here lies a young galaxy. We knew the first ones formed a few 100 million years after the Big Bang, but the details were blurred. The arrival of more powerful infrared telescopes changed the landscape. Suddenly, the early universe was no longer a shadow. We began to see structure, shapes, richer spectra, signs of gas, stars, and dust where we did not expect so much. The key point is redshift. Light from very distant galaxies reaches us stretched by the expansion of the universe. What was originally ultraviolet or optical arrives as infrared. To detect it, we need instruments sensitive to those wavelengths. That is where these new observatories become decisive. What we began to find at very high redshifts was puzzling. At epochs when the universe was less than 1 billion years old, there were already galaxies with substantial stellar mass. Some showed signs of significant metallicity, others were full of dust. They were not primitive, clean clouds. They were systems that seemed to have lived through several stellar generations. This creates a direct tension with our expectations. In the standard framework, the first structures grow from small density fluctuations. Gas accumulates in dark matter halos. It cools, it forms stars. The first stars are massive and short-lived. They die quickly, enriching the medium with heavier elements. Then come later generations, born in an already enriched environment. This process takes time, not centuries or millennia. It takes hundreds of millions of years. If, despite that, we find very distant galaxies that already possess substantial mass, metals, and dust, an immediate question arises: was there enough time? Several explanations are possible, and they are not mutually exclusive. One is that star formation in some environments was far more efficient than we assumed. Perhaps certain regions of the early universe collapsed rapidly, concentrating gas and triggering intense bursts of star formation. In that scenario, a few massive generations could have enriched the medium in a short time. Another possibility is that we are underestimating observational effects. Determining the stellar mass of a distant galaxy is not simple. It depends on stellar population models, on assumptions about the star formation history, on how we interpret the dust that dims the light. A change in those assumptions can alter estimates. Some galaxies that appear extremely massive may, in reality, be less extreme. Sample selection also plays a role. Surveys more easily detect bright galaxies. That can bias the picture toward the most extreme cases. It is natural that, looking far away, we find the most active, the most luminous, the dustiest ones. We are not seeing an average, we are seeing the tip of an iceberg. Even so, the collective signal points to something real. The early universe was not a slow and timid phase. It was a period of intense activity, vigorous star formation, rapid growth of structures, circuits of gas and radiation in constant interaction. Dust is a strong indicator of that process. It does not appear out of nowhere. It forms in the envelopes of old stars and in supernova explosions. Seeing a great deal of dust in very young galaxies implies that several stellar generations had already lived and died. That requires an accelerated history. In addition to dust and metals, there is the question of morphology. Some very distant galaxies appear compact and dense. Others show irregular structures, as if they were in the midst of merging. In both cases, the picture is that of a dynamic ecosystem, not isolated objects forming in calm conditions. This connects with another protagonist of the early universe, supermassive black holes. In several of these young galaxies, active nuclei are detected, signals of gas falling toward a massive central black hole. This further complicates the picture. It is not only necessary to explain how galaxies grow, but also how the black holes at their centers grow, almost at the same time. The relationship between black hole mass and stellar bulge mass in nearby galaxies suggests co-evolution. Galaxy and black hole grow together. If we see very massive black holes in the early universe, this implies that efficient channels existed either to form large seeds or to feed them at high rates in a short time. All this leads to a reformulation of the questions. Instead of asking when the first galaxies formed, the issue becomes how fast matter could organize itself in specific environments. It is not that the basic model of gravitational collapse is wrong. It may be that we underestimated how quickly certain regions could turn into star factories and black hole nurseries. At the same time, the discovery of these mature galaxies in the young universe forces a revision of cosmological calibrations. The history of structure formation is tied to the history of expansion. If space stretched at a given rate, there was a certain time window for galaxies to grow. Changing the rate, even slightly, affects that window. Here, the connection with dark energy and the Hubble tension becomes evident. If the current Hubble parameter turns out to be different from what was thought, or if dark energy was not exactly constant, then the entire diagram of available time for structure formation is altered. Some tensions between theory and observation could be eased in that context, or conversely become more acute. Another important aspect is the role of environment. The early universe was not uniform in practical terms. There were denser regions where matter collapsed earlier and emptier regions where collapse occurred later. It is not surprising that we are seeing precisely the advanced regions, the first cosmic neighborhoods to fully light up. What is striking, however, is the number of these advanced cases. How many dusty, massive and active galaxies appear at very high redshift? If they are few and rare, they can fit as extremes of a distribution. If they are many, the tension with standard simulations grows. The answers are not yet definitive. The samples continue to expand. Analytical methods are being refined. Models of star and dust formation in the early universe are being improved. What was once interpreted as a crisis may turn into a minor correction, or, on the contrary, it may solidify as a sign that some physics is missing from the picture. Supermassive black holes. At the center of many galaxies, there is an object that, at first glance, does not fit any familiar scale. A supermassive black hole, millions or even billions of times the mass of the Sun. It occupies a small region compared to the size of the galaxy, yet it influences everything around it. The basic question is simple: how do you get something so large in such a short time? We know that black holes form under normal conditions as the remnants of massive stars. A star much heavier than the Sun runs out of fuel, explodes as a supernova, and leaves behind a collapsed core. That core can become a black hole of a few solar masses. This is the best known formation channel. If we started only from the stellar remnants and let them grow by accreting gas at modest rates, the path toward billions of solar masses would be long. Too long for certain cases we observe in the early universe. There we find supermassive black holes when the cosmos was less than 1 billion years old. The available time is limited. To understand the problem, we have to talk about accretion. A black hole grows when matter falls toward it, gas, dust, stars. Before crossing the event horizon, the matter forms an accretion disk. It heats up, it emits radiation. That radiation exerts pressure on the gas still trying to fall inward. A balance develops between what falls in and what the radiation pushes away. That balance defines a maximum sustained growth rate, the so-called Eddington limit. A black hole can exceed this limit for short periods, but it is not easy to maintain for long. The classical idea is that even growing at the maximum allowed rate, a minimum amount of time is required to go from a small seed to a supermassive monster. Some observations show that if those seeds are very small, the time is not enough. This leads to the hypothesis of large seeds. Instead of starting only from stellar remnants, the early universe may have produced much more massive initial black holes. For example, through the direct collapse of primordial gas clouds that, under certain conditions, avoid fragmenting into stars and collapse almost all at once. In that scenario, the initial seeds could already have tens of thousands of solar masses or more. This drastically reduces the time needed to reach supermassive scales. After that, accretion and mergers between black holes would complete the process. Besides the seeds, the environment matters. A black hole embedded in a region with abundant cold, dense gas can feed more efficiently. Galaxy mergers help. When two galaxies approach each other, their gas clouds are compressed, bursts of star formation are triggered, and at the same time, gas is funneled toward the center. That feeds the black hole. In the early universe, mergers were more frequent. Galaxies were more compact. Gas was more abundant. All of this favors phases of rapid growth for central black holes. We do not see the entire process, but we do see its consequences. Intense, active galactic nuclei, bright quasars, signatures of hot accretion disks that dominate the galaxy's luminosity. The presence of a supermassive black hole is not a local detail. Through its activity, it can influence the gas cycle of the entire galaxy. When the black hole feeds, it launches relativistic jets. It expels winds. It heats the surrounding medium. This feedback can suppress the formation of new stars, expel gas into the halo and even into intergalactic space. This mechanism turns the black hole into a kind of regulator. It not only grows, it also moderates the growth of the galaxy that hosts it. Not always, and not in every system, but on large scales, statistics suggest a relationship. Galaxies with more massive bulges tend to host more massive central black holes. There is a correlation that does not appear to be random. In galaxy clusters, this effect is visible in the hot gas between galaxies. Jets from central black holes can carve cavities in that gas. These cavities appear in X-ray maps. They are traces of episodes in which the black hole returned to its environment part of the energy it received while feeding. In this way, the problem of impossible growth connects with large-scale structure. We are not talking about isolated objects, but about key pieces in the cosmic ecosystem. Without the effect of black holes, simulations often produce galaxies that are too massive or with star formation histories that do not match what we observe. The question remains how all these pieces fit together in the early universe. Large seeds, frequent mergers, accretion phases near the Eddington limit or briefly above it, dense environments where gas can fall rapidly toward the center. Each ingredient helps, but the full puzzle is not yet solved. Moreover, many of the most extreme supermassive black holes are detected through their activity as quasars. That introduces biases. We see the most luminous cases, those in a phase of intense accretion. There is likely a significant population of supermassive black holes that spend most of their time in a quiet mode, detectable only through their gravitational effect. Understanding this hidden population is another challenge. Measuring masses through stellar dynamics, using broad emission lines, studying how they are distributed across different types of galaxies. All this feeds models that attempt to reconstruct the growth history of black holes over cosmic time. But there is a different way to study their evolution, one that does not depend on light, a path based on gravity itself. If supermassive black holes grow not only through accretion but also through mergers with one another, each merger should shake the fabric of space-time. It should generate gravitational waves. On stellar scales, we have already detected these waves, mergers of black holes with tens of solar masses, brief, high-frequency signals. For supermassive black holes, the music is different. The frequencies are much lower. The periods span years. Individual signals are difficult to separate, but all of them together, accumulated over the history of the universe, should produce a gravitational wave background. That background would be a kind of permanent hum in space-time. It cannot be detected with interferometers like those used on Earth for stellar mass mergers. A different technique is required. One must use pulsars as extremely precise clocks and look for tiny correlations in the timing residuals of their pulses. If we manage to measure that background, we will not only confirm that supermassive black holes merge as expected, we will also obtain direct information about the merger rate over time, the population of orbiting black hole binaries, and how they contribute to the overall growth of these cosmic monsters. A noise coming from the depths. Until now, we have seen the supermassive black hole as a luminous devourer, a beacon, a violent regulator of its galaxy's gas. But there is another side, one that cannot be seen in light, one that only appears if we listen to the very fabric of space-time. When two supermassive black holes orbit one another, they are not still, they rotate slowly, they deform space. That deformation propagates outward in the form of gravitational waves. They are real ripples of space-time. Nothing travels inside space. It is space itself that vibrates. In mergers of stellar mass black holes, those waves have relatively high frequencies, milliseconds, seconds. We can detect them with interferometers such as LIGO or Virgo, measuring tiny changes in the distance between mirrors, separated by kilometers. With supermassive black holes, something different happens. Their orbits are enormous, their periods are extremely long, the gravitational waves they generate have extremely low frequencies. They do not oscillate hundreds of times per second. They do so once every several years. They are very low notes in the symphony of the universe. We cannot detect those frequencies with the same instruments. We need cosmic clocks distributed across the galaxy, objects that emit regular pulses for years and years. Those clocks exist. They are millisecond pulsars. A pulsar is a neutron star that spins at high speed and emits beams of radiation. Each rotation produces a pulse. If the beam sweeps across Earth, we observe an extremely stable periodic signal, so stable that we can use it as a time reference. Now imagine that a gravitational wave with a period of years passes between us and several pulses. That wave stretches and compresses space in different directions. The pulses no longer arrive exactly when they should. Small variations appear in the arrival times, correlated among different pulsars depending on their position in the sky. The idea of a pulsar timing array is precisely that, observing many millisecond pulsars over many years. Recording the arrival times of their pulses with extreme precision, searching the data for common patterns indicating that space-time is vibrating coherently, we do not expect to see individual, sharp waves from a single merger. What is first sought is a background. The sum of the waves from thousands or millions of pairs of supermassive black holes orbiting throughout the universe. A collective hum, a fog of slow waves. If that background exists and is strong enough, its statistical signature should appear in the data, not as a sudden rising signal, but as a subtle correlation in the pulse deviations, a kind of background music recorded in cosmic clocks. For years, different consortia observed pulsars searching for that imprint. The data accumulated slowly. There were hints, growing but inconclusive signals, until recently when several groups announced results consistent with the detection of that low-frequency gravitational wave background. What does this mean? First of all, it confirms that pairs of supermassive black holes are common. It is not just theory. The universe is full of galaxies that have merged or are in the process of doing so. Every major merger can leave behind a pair of central black holes orbiting for a long time before they finally come close enough to merge. Those pairs, distributed throughout the cosmos, contribute to the hum. The intensity of the background gives us clues about how many there are, what their masses are, how they evolve. It is an indirect way of counting mergers that we will never see in light. Secondly, this background opens a new window onto the history of large-scale structures. Every galaxy merger is linked to the growth of filaments and clusters. Listening to how many supermassive black hole mergers have occurred at different times is, in essence, listening to how the cosmic web consolidated. Thirdly, the spectral shape of the background may tell us whether there is something more exotic mixed in. For example, topological defects in spacetime or phenomena in the very early universe that could also generate low-frequency gravitational waves. For now, the simplest scenario is that of black hole pairs, but the door is open to explore alternatives if the signal does not perfectly match expectations. What is interesting from an extragalactic perspective is that these slow waves allow us to connect scales. A pair of black holes orbits on subgalactic scales. However, the signal it produces adds to that of thousands of other pairs distributed across superclusters and filaments. The final result is a background that speaks to us about the entire universe. Moreover, this technique does not stop there. In the future, if we improve precision and expand the number of observed pulsars, we could begin to separate individual contributions, identify specific pairs of supermassive black holes as dominant sources, follow their evolution over time, combine gravitational waves and electromagnetic observations to reconstruct precise histories of extragalactic mergers. All this illustrates a paradigm shift. For a long time, cosmology was built on maps of light, galaxies, clusters, microwave background. Now, we are beginning to add maps of gravity in the form of waves. They do not replace the previous ones. They complement them, they correct biases, they provide different information. The low-frequency gravitational wave background is, in a sense, the noise of the machinery of the universe on large scales, the echo of the constant reorganization of matter in galaxies and clusters, a reminder that what we see as fixed structures is actually the product of dynamic processes that are still ongoing. And here a link appears with another aspect of the large scale that at first glance seems very different: the role of voids and galaxy flows. So far we have talked about what comes together: mergers, collapses, dense filaments. But the universe is also defined by what is missing, by regions of very low density that grow over time and that, in a sense, push galaxies toward denser areas. Cosmic voids and the great attractor. When we think about cosmic structures, we usually imagine clusters of galaxies, dense regions, places where there is a lot. But on large scales, the universe is not dominated by what is abundant, but by the combination of what is very full and what is nearly empty. Cosmic voids are an essential part of the gravitational landscape of the cosmos. A cosmic void is not a perfect hole. It is not a space completely devoid of matter. It is a region where the density of galaxies is much lower than average. There may be a few isolated galaxies, very tenuous gas, diluted dark matter, but compared to a filament or a cluster, it is almost a desert. These voids can be enormous in size, tens, even hundreds of millions of light years across. They are not perfect spherical bubbles, although they are sometimes represented that way in diagrams. They have irregular shapes. They connect and chain together. They are part of the same sponge-like pattern we see in the cosmic web. What is interesting is that voids are not merely what is left between the important things. They are dynamic actors. In the history of the universe, regions that were slightly less dense than average became emptier still. Matter flows from voids toward filaments and nodes. Over time, voids become emptier and dense regions become denser. From a gravitational point of view, this has consequences. A galaxy located between a massive cluster on one side and a large void on the other feels both effects. The cluster pulls it. The void, having less mass than average, is equivalent to a push in the opposite direction, not because the void actively pushes, but because there is more gravity pulling from the side where matter is present. The result is that galaxies do not only fall toward great attractors, they are also expelled from voids. Large-scale matter flows are the combined product of these two influences: attractors that pull, empty regions that cease to retain. We can think of the universe as a landscape: hills, valleys, plains. In that landscape, matter rolls downhill toward gravitational valleys, which are clusters and superclusters. Voids would be the hilltops, the regions from which everything tends to fall away. As time passes, the valleys deepen and the peaks erode, becoming increasingly cleared of matter. When we observe the peculiar velocities of galaxies, that is, their additional motions apart from the general expansion, we see patterns. Entire groups move in preferred directions. These motions cannot be explained solely by a single isolated massive object. They are the response to the full topography of matter and the absence of matter across a large region. For years, astronomers spoke of great attractors, regions of high density toward which many neighboring galaxies seem to be heading, including our own. These attractors are not mysterious magnets. They are massive concentrations of clusters, filaments, dark matter, and gas. In their surroundings, voids also play a role, allowing matter to flow more easily in certain directions. Our own local group is not at rest with respect to the cosmic microwave background. It moves, it is part of large-scale flows. It is pulled by the gravitational landscape of nearby superclusters and, in a sense, pushed by neighboring voids. This collective motion reminds us that our galaxy is not static, not even on intermediate cosmological scales. Measuring voids is not trivial. To identify them, one must map the distribution of galaxies with sufficient depth and angular coverage. Once the map is constructed, algorithms are applied to find connected regions of low density. These algorithms must deal with incomplete data, areas obscured by the Milky Way, and brightness limits. Once catalogued, voids become tools. Their size, shape, distribution, and the way they grow over time are sensitive to cosmological parameters. The total amount of matter, the nature of dark energy, and the behavior of gravity on large scales. All of this leaves imprints on the pattern of voids and on how they empty out. In fact, voids offer an interesting laboratory for testing whether gravity behaves exactly as expected from general relativity. In very low-density regions, certain alternative theories of gravity might show slightly different effects from the standard theory. Comparing predictions with observations in voids provides a complementary approach to tests performed in clusters or in the cosmic microwave background. Voids also affect light. When a photon crosses a region that is less dense than usual, the way it gains or loses gravitational energy can differ subtly. These effects, integrated over many voids along the path, contribute to small variations in the temperature and polarization of the cosmic microwave background, another way of detecting their influence without seeing them directly. The fact that the universe is filled with enormous voids and dense filaments forces us to abandon the idea of a uniformly filled cosmos. Large-scale homogeneity does not mean that everything is evenly distributed everywhere. It means that if we look at sufficiently large volumes, the average statistics become uniform. Within those volumes, however, the structure is highly pronounced. An important intuition emerges here. The size and depth of voids are linked to the time matter has had to evacuate those regions. The longer gravity acts in an expanding universe, the more pronounced the contrasts become. If the rate of expansion changes, the history of voids changes as well. In a universe dominated by dark energy, accelerated expansion tends to freeze the growth of structure on very large scales. Matter continues to flow locally, but beyond certain sizes, the stretching of space wins out. Voids that already exist continue to grow somewhat, but new giant structures no longer have the same room to consolidate. This suggests a picture of the distant future in which the universe appears increasingly fragmented. Islands of bound matter, such as groups and clusters, become isolated from one another by oceans of accelerating expansion. The voids between them widen, effective gravitational communication diminishes. What we now see as a connected cosmic web becomes, over very long timescales, a set of disconnected archipelagos. From our current perspective, we are still living in an era rich in connections. Large-scale flows, voids and attractors combine to shape the map of galaxy motions. Each new deep survey adds detail to that map. It refines measurements of the gravitational landscape. As these maps improve, they intersect with other sources of information, low-frequency gravitational waves, gravitational lensing by galaxies and clusters, where the light from background objects bends as it passes near concentrations of mass, maps of hot gas in X-rays, maps of the cosmic microwave background. Everything fits, or should fit, into a coherent picture. If something does not fit, that is where the real mysteries appear. Discrepancies between the rate of expansion and the pattern of voids. Differences between the expected growth of structure and what is observed. Signs that perhaps dark energy is not as simple as we believe, or that dark matter has properties not yet considered, or that gravity itself requires subtle adjustments on large scales. The universe beyond the Milky Way, seen in this way, is not merely a catalogue of exotic objects. It is a complex system in dynamic equilibrium between what accumulates and what empties, between filaments that grow denser and voids that expand, between clusters that attract and matter-poor regions that cease to retain. Our galaxy is a particle in that flow. It is part of a group falling toward larger structures, while at the same time moving away from others because of accelerated expansion. It travels through a landscape sculpted both by luminous great attractors and by enormous, almost invisible voids. When we speak of mysteries beyond the Milky Way, we are really speaking of this, of our difficulty in reconstructing from fragments of light and tiny ripples in space-time the full design of a network that extends far beyond anything we will ever be able to visit.